is Janet Lenihan, and I have the great pleasure of serving as Dean of the Frank G. Zarb School of Business, and we are thrilled to have all of you with us today for what I know is going to be an incredible behind-the-scenes look at the development, launch, and operations of the Webb telescope. And today's talk is really about innovation and the incredible technological advances and engineering that made the Webb telescope possible. But before we delve into the exploration today and all of the great discussions that we are about to have, I want to first take a moment to thank Doug Main. Doug is not only an alum of the Frank G. Zarb School of Business, he serves as chair of our advisory board, and it is thanks to him that we have Mr. Willoughby here with us today. And you know, not only is Doug just unwavering in his support of our students and our school, he's a great mentor to me and a leader for the school, and so please join me in thanking him for being here and making today possible. We have a few housekeeping items. First, there can be no videotapes through your phone. We have Mr. Brian Potts here and his crew, so they will take video recording, and we will get that uploaded and everyone will be able to have it. But more importantly, put your phones away and really take the time to enjoy this presentation and discussion. I can tell you it's incredibly fascinating, and our speaker today is not only passionate about what the telescope has done and can do. You will learn so much from what he has to share with us. Second, we will definitely leave plenty of time for question and answers, and so what I will ask you to do is think about them, and when the time comes for an opportunity to ask your questions, please find your way to the microphones on either aisle, and please make sure you ask your question in the microphone. I will ask you also to please introduce yourself, give us your name, and what your major is. That will certainly help make it more of a conversation, which is what we want to have happen today. And lastly, for all of the students, make sure that you have scanned the QR code and have registered for your attendance here today. We want to make sure that your professor knows you're here and you're not sitting with your classmates. And so really put away your cell phones and take the next hour to enjoy what truly will be a cosmic experience, and I'm looking forward to it. So now it's my great honor to introduce someone who truly embodies an innovator's mindset. He has sparked creativity and innovative thinking across our academic enterprise, our very own provost, Dr. Charlie Reardon.
Good morning, everyone. My pleasure to add my welcome as well. So Janet, thank you very much. Dean Lenihan, Doug, thank you for all of your leadership and steadfast support of Zarb School. So it is really an exciting day for me. It's kind of the culmination of what I call Geek Week. So Geek Week, as you may know, the last week we've heard about the announcement of this year's Nobel Prizes in a variety of disciplines, including this morning's announcement of the Nobel Memorial Prize for Economics. And the other prizes, you know well, literature, Peace Prize for the end of last week and at the beginning of the week were the prize for physiology and medicine, physics, and then chemistry. And so it's on the heels of all those great discoveries that we understand the human condition much better. And so it's through the development of technologies like you'll hear about today that we understand the human condition and the world about us much better. So a little bit about our visitor today. Scott P. Willoughby is the Vice President of Performance and Operational Excellence, serving Northrop Grumman's space systems sector, a leading provider in the space and launch systems that serves national security, civil and commercial customers. Prior to assuming this role, Mr. Willoughby has held the role of the Vice President and Program Manager for the James Webb Space Telescope, overseeing all aspects of the program, and it's that work in that capacity that primarily he visits with us today. As you may know, the James Webb Space Telescope was launched on Christmas Day 2021, and since the following January has been orbiting the sun about 1 million miles from Earth. As recently in the past few days, it's been reported that the Webb telescope, which is a near-infrared detector, has discovered carbon dioxide at specific locations on one of Saturn's moons, Europa's icy surface in a region called Terra Regio. Interestingly, in the connection to the James Webb telescope, it was the famous Italian scientist Galileo who used his homemade telescope to first identify Europa in the year 1610. Throughout his long career, Mr. Willoughby has accumulated broad experience across many areas, including systems engineering, integration, testing and launch, antenna products, project and functional management. He was the director for integration, test, and launch within Northrop Grumman Space and Technologies Production and Supply Chain Organization, where he focused on improving best practices across those program sectors. He joined Northrop Grumman right out of college in 1989 as a member of the technical staff for TRW, which is a heritage Northrop Grumman company. He received his bachelor's degree, summa cum laude, in electrical engineering from Lehigh University in 1989, as I mentioned, and then a master's degree in communication systems from USC, Southern California, in 1991. Mr. Willoughby is also a graduate of the UCLA Executive Program at the Anderson School of Management, and as you will hear in just a few seconds, is an outstanding communicator of technology and discovery in broad ways that make it very accessible to all of us. So it's a great pleasure to welcome Scott Willoughby to Hofstra University.
I'm also a wanderer when I talk. So thank you, Dean, Provost, and Doug, who I got to meet and complain about the Yankees the entire season with. Just so you know, you always have to have something else to talk about. Coming onto campus was a bit intimidating for me. This is somebody who's spoken to Congress every 3 months for the last 10 years, run an $8.8 billion space telescope, had had a chance to present in many audiences, but I felt like I hadn't done my homework. So anyway, you're supposed to laugh at that, right? You know, come on, go on campus, it's gotta be, you know, everybody who woke up this morning hadn't done something they were supposed to do. I feel the same way. What I really do want is to talk to you about a project that I believe has already, actually in its journey, but even more so now in its results, inspired a world. And science tends to do that. And any moment I get a chance to share what's going on is a special moment to me. But I feel this is a two-way kind of agreement here. I came here because I want to tell you what's going on. I also want to hear what you want to ask. At the same time, my ask for you is, when you leave here, talk about what you heard. Tell your friends who weren't here what you learned. I guarantee I'm going to put a few fun facts in that you will know that the people outside of this room won't know. I'm going to translate that to you in English. And if you share that, you're going to inspire one or two or three, right? And then the butterfly effect happens.
have a fully deployed JWST observatory.
really faint. We run that mirror at minus 388 degrees Fahrenheit. Minus 388 degrees Fahrenheit. It's only 38 degrees above absolute zero on the Kelvin scale. And we actually run one instrument at 6 above absolute zero. But so we have to make it cold. We created this big parasol umbrella before that. Let's put it in the canister. Well, we can't put it in the canister because that won't fit in the top of the rocket. So for years before we even won the program, people were scratching their heads with concepts. But this is what drove, right, that idea of purpose. And our purpose was find out about the early universe. How did it form? Everybody in this room, I guaranteed, if you were only 13.5 billion years old, would have gotten an A in chemistry. Super easy. Who had trouble with chemistry in here? Raise your hand. Well, I got to get a lot more hands than that. Well, you're Hofstra. Got it. Only half of the room, right? The periodic table is very complicated. It started off with elements 1 and 2. Hydrogen and helium. I won't quiz you guys what those were. Sometimes I like to mess with the audience. 1 and 2. It was as simple as that. The reason we have the substance and the elements that Earth and our bodies consist of is because fusion. Elements being burned together and fusing themselves and building the periodic table up. Building it up through a star. That's what it is. It's a fusion reactor. And then those stars explode and they create heavier elements. So we're looking back to see how that happened. All of that light, I can keep going on and on, is now in the infrared spectrum. Started off in the ultraviolet, it got stretched by the expanding universe, and now it's there, and we had to go find it with this very cold optic. How did they evolve over time? How did they get to the present time? How did these stars have these life cycles? And then the very last part, the origins of light. Not only the origins, but does it exist somewhere else? Are we alone? We literally have an instrument that can look into the atmospheres of planets around other stars now and try and find the fingerprint of what an Earth atmosphere looks like and say, oh my gosh, maybe life would exist there. Truth be told, we'll never be able with the Webb to look on the surface of that planet and find if there's life there directly. That's what you guys, as a part of the team, and whatever role you play, will get a chance to do. And I always said that next telescope that looks on the surface of that planet to see if there's life will know there's intelligent life if they find Yankee Stadium. Good, you can chuckle because that is a bad joke today. It was much better 10 years ago when I told it and I had just won a World Series. So, this is what we're trying to do. Purpose, folks. Lead with purpose. The challenge was this innovation. This innovation was by being limited by parameters that were immutable at that point in time. We weren't going to go figure out the bigger rocket and the bigger fairing and say, well, you want a bigger telescope, let's go solve this equation first. That wasn't the investment we were taking on. So we said, how do we deal in a constrained fashion with it? And had engineers come up with something that can fold. And the reason you have to be larger, right, it's a fun fact. Collecting light in the sky, photons, is effectively like collecting raindrops when there's in a drought. Does it matter if you have a ½ inch of rain how deep your pool is? No. Does it matter how wide your pool is? Yes. Right? Glass, this, that, a barrel. So the bigger the optic, the more photons, the more raindrops coming off of these old stars we're going to collect. Therefore, the more science we can do. Infrared, I already told you, that first starlight has been stretched into the infrared. The same way that sound stretches when it goes away from you and the Doppler effect. You only know that by you stand on a street corner. Why does that car go vroom, vroom? Why does the noise change? You're in the car. Noise isn't changing. It changes because sound stretches when it goes away from you. When the universe expands, light stretches, stretched into the infrared. Little trick because of that whole idea of being masked out by thermal data out there. Minus 388. We're literally inventing glues and materials that could perform at minus 388 and not break, not being brittle, not that. Stable. You've got to stare at these objects for a long time still to get these things. Lightweight. Hubble, 25,000 pounds. Went on a space shuttle belly 300 miles away from us. You know, Hubble, when it goes overhead, is closer than, I don't know, it was easy to say from Los Angeles to San Francisco. Maybe a little bit further than DC. Literally only 300 miles overhead. Webb, 1,000,000 miles away. Further you got to go, the lighter you have to be or the stronger your rocket has to be. We were 14,000 pounds. 25,000 pounds for this single piece of optic and Hubble, 7 times bigger, half the mass. And then, like I talked about, going far away. We had one shot. So we built a foldable telescope. There's that mirror you saw on the first page, except what's missing? They're missing the sides. All the sides are folded back if you kind of peek on the left side there. The thing that the light bounces off of and then bounces out and then comes in, the nose of that, is folded up and above it. But underneath it is that big umbrella that is going to deploy in front of it and get it to minus 388. Because the hot side, the underside of that, when we're in sunlight, which we perpetually are, plus 188. About 600 degree Fahrenheit differential. If you do the math, it's an SPF of over 1 million if you go to CBS. That's our sunscreen. We built it into that. That sunshield does not fit 16 feet across. Folds up like a parachute. Gets affixed to 107 release devices, 90 cables, 40 pulleys, something like that. All of that has to work. They're all called single point failures. So we built an instrument that looked like that. I think this one, just for a quick video shows, in order to do that, we don't just do that as NASA and Northrop Grumman. We literally did that practically around the globe. Everything that's written in there is a company, and it's not fully representative, that had something to do with build a part, and a significant amount from the Canadian Space Agency and the European Space Agency. So really on top of the $8.8 billion that taxpayers in the US put in this, about another $2 billion came from international contributions to this. So when you hear it's a $10 billion telescope, that's what it means. It means taking the whole economic into that. The favorite part of this picture for me, an optic there or somebody under there, is people. But none of this happened with just brilliant minds sitting in a conference room. People bunny suited up, and long before masks were in vogue, we already knew how to wear masks because we're in a high bay where contaminants from our voices, just our mouth, right, and what comes out, or from our bodies and our hair and all that kind of stuff, could affect this optic because it's so perfect you can't afford to have dust on it or anything. So we have people in bunny suits underneath here putting in cables and clips and massive, technology and bringing this together into a form that can launch and go into orbit 1 million miles away. This is another viewpoint of somebody folding that sunshield. So I told you it started out, right, or it finishes on orbit in that big kite-sized thing, which is literally probably almost 80 feet long by 40 feet wide, but it has to be folded up by technicians and then pinned. My favorite story in folding that sunshield was that when we tried to do it the first time to deploy, we got tears in the sunshield. And we looked at it and we said, well, how did that happen? We can't see that. And in order to hold the sunshield together, we have holes that have to be aligned and a pin has to go and it secures it, right, for this violence of going into orbit. And those holes, sometimes 55 of them stacked, weren't perfectly aligned, so when the pin comes through, you can imagine one's a little bit off. It's got to rip them, right? It's got to make little tears in it. And we couldn't solve that problem. I got some of the brightest PhDs in the world working there. The technician on my team went into his tackle box and said, I got this thing called a squid jig. It's got little soft legs, and it goes like, what if we put it in on the other end on the string, and then we pull it back, and when it comes through that hole, it'll knock all those holes in alignment. It'll be confined enough not to tear them, but it'll be strong enough to push them out. Because that technician raised his hand and was comfortable enough speaking in an audience of folks that could have been intimidating and said, I got this thing in my tackle box, we learned how to fold a sunshield. My message is, do not shut out any voice in solving any problem. Don't ever try and be the smartest person in the room that walks away and felt like you were successful because you walked out and people were intimidated by what you said. And therefore they shut up and you're just the expert. If you aren't engaging folks and people aren't coming back and telling you things, raising their hands and questioning what you say, you're failing. You're never going to do something great. You're not going to get there on your own. We created an environment to invent, survive failure, build it better, an environment where people can talk to each other, right? Where they can raise their hands and they can feel comfortable. I know you're at the age right now where you're the hand raiser. You're going to be at that age where you're the ear listener. And you're going to do that in your groups. And just keep thinking about that. It's one of the things I was talking a little bit to the dean and the provost about is I had to talk to Congress every 3 months for 10 straight years. And the last thing I wanted to do was have people continue to fund an $8 billion project by intimidating them. I wanted to do it by having them care about the purpose, why we're doing it, and the humility of why it's hard, but also the confidence of why we're going to be successful. Not by intimidating them with technological terms they couldn't understand. So piece this stuff together, right, as you're going forward. Trust me, I wasn't that smart when I was in your chairs. And telling me backwards, that worked out pretty well. So but put it into your repertoires. This is then as we're folded up. And literally, that picture I had him put in there, because it was the scariest day. When we take this thing, and it's affixed to there, and we built it in a vertical form, and we had to lower it to put it in a shipping container, because it's easier to get out the door on its side than it is tall, and then put it on that boat on there, and I'm standing in the window, and this thing is tilting sideways, sideways, sideways. Then you want to make sure all the bolts are put in the right place and torqued down pretty good, right? Because you've got this, literally. But it's designed to go in that ring and go in that thing that's sliding down, called that payload fairing. That's the thing that protects it, right, as it's getting ready to go into orbit. And I happen to have the chance, the privilege to be there in French Guiana. So I went inside those shower curtains. I didn't get to put a cool yellow suit on. I was in the visitor one. They always put the people who don't belong in another color hat. So they know not to let you too close to it, right? So I would have been off to the side, but I got to get a chance to be in French Guiana, and I was there on Christmas Day. In the video, there was the guy with the picture and the thumbs up with the bald hair and the mask. No, that wasn't me. My daughters kept saying, "Why did they keep calling you Jean-Luc Dad?" I'm like, no, that was the French guy. I was the other person in there. So, but if you wanted to think I was the bald-headed person going like this on that video, it's cool. Tell your friends. You might know it. So this is that complexity of web after being fully deployed, and it's really hard to show you other than animation of it being stowed up with 344 single-point failures. One goes wrong, mission ending. Encapsulated into the top of that rocket, this all happened on Earth and in there. Launched, and as we're traveling 1 million miles away from Earth, as we're moving in space, we start this unfurling, this beauty, this origami in terms of coming apart, of the sun shield opening long, of a balanced, tab, solar tab at the back, as covers opening up so that the sun shield can get pulled wide on two sides. The sun shield is 5 1,000th of an inch thin layers of Kapton with thermal coatings to block this 200 degrees Fahrenheit and vent it out. Of the nose of the mirror coming out. The radiator in the back to get rid of heat, of a wing coming out, of a wing coming out. And this Webb telescope fully deploying into its full size, bigger than anything ever put into space in the form of a science instrument. And it's the first not only deployable optic, it's the first adaptive optic. We also wanted to give ourselves a degree of freedom such that if we were imperfect when we got there, every one of those hexagonal mirrors has 7 motors on the back. 1 on each corner, and 1 in the center of curvature. Actually, every 2 weeks, we keep fixing our prescription on the Webb telescope with an adaptive optic. We take data from the instruments, and we do what's called tip, tilt, and piston. All 18 mirrors have to be in the same plane. It's not plane because it's it's concave, but they all have to act as a single mirror. And if they're out of phase, the photons will be confusing as they come through. So we can do that, and we can actually change the center of curvature. So we not only made a deployable optic, we made an adaptive optic, which is super cool, which means for the life of this program, we're going to have about the same accuracy at the beginning, other than micrometeorites kind of doing little ticks in the optic there. So here's some videos, though, of the awe of what happened. That before and after was a Hubble shot, or in this case, a Spitzer, the best infrared shot, and then what Webb saw. So as we go there, I'm going to go back, but I like it. Hubble, pillars of creation, Webb staring through that stardust into stars being formed. Spitzer, the greatest infrared telescope before Webb, taking the blindness out there and literally seeing every dot in there being another galaxy that we didn't know exist or didn't have any direct information on, because we built an instrument to improve so greatly. This was not, one of the things I tried to tell NASA, I'm going to love this as a picture as my Dropbox, the hack drop, One of the things that NASA Northrop, told the public was that the reason we are having such struggles in building this telescope, because we were, and you Google Webb in Willoughby, and that's pretty cool. You'll see me, and you'll say, hey, I met that guy. Remember when I first started dating my wife, I said, I told my friend your name, and they said, oh, he's Googleable. Well, that's pretty cool, right? You got out there. Some of those articles aren't so pleasant, because they were really describing, right, the journey that we had and the failures in there. We had failures because we weren't trying to do something that was an increment better than the prior thing. We had run out of the ability to make Hubble a little bigger, because it still was only going to be in the optical range. To take the Spitzer and do something. We had to make something that stepped. It was the revolution versus evolution, if you've heard those terms. And in there, I didn't think it was going to go perfect. But again, there's a context when I say that to you. If I told you to do something, take something that's already great and make it a little better. You're going to think, and you yourself are going to have a more expectation that it's going to go a bit more perfect. It's still going to be challenged, right? Because you're doing a little, but you're 95%, right, of prior and stretching it. Again, back to what that purpose was. Purpose wasn't only scientific, it was to create an instrument that we didn't have something to make better before. We didn't have a deployable telescope. We didn't have one that operated at -400 degrees. So we were doing revolutionary science. And when I explained that the instrument itself was revolutionary, because people were spoiled with Hubble and Chandra and all these things, as if just keep doing greatness. And I get it, they had their own bumps in the road. But people tend to forget the bumps, after the science comes. Like, why don't you just do that a little bit more? We had to express to people what was difficult in our journey. Remember, as you're out there innovating, creating new products, to your consumers, think of it. Are you making something a little better? That's great too. Or are you making something that wasn't a step in the equation, right? It goes like this. It isn't just the next dot on the line. Describe it that way. People will understand your journey better, right? Put it into English so people know. We were a revolutionary telescope. When this became probably the most iconic screensaver in there. And this horizon, and as we see through there, we're actually seeing what are called stellar nurseries. We're seeing stars being born, because infrared is transparent. It's kind of like an X-ray. You can go through your skin and see the bone on the inside. The infrared light goes through. The optical, it's opaque. It can't get through. This image, and one of the things to point out, just so you're smart in the room, like if people are showing science images and in there, and you look, of course, there's quite a bit of it, but not nearly as much as 30 years of Hubble. See those 6 points right there, the major? There's a couple of thin ones going horizontally out, but those 6 points, because of the 6 sides of the hex mirror and that aberration, you'll know it's a Webb picture if you see the 6 spikes, so with the thin ones. So if you see the 4 spikes, that's a Hubble mirror. We actually had a presentation that somebody gave out, and they gave me a picture, and I'm like, that's a Hubble picture. I'm doing a Webb presentation, right? It wasn't before. So you'll have fun. I don't know how many opportunities you're going to have in your life to say, hey, I know that's a Webb picture and why, but if you do, take advantage of it in the moment you have. Impress your friends. This picture right here, when this came forward, this is one of the first pictures, and if you go back into that video in your brain, it came by real quick, but you would have saw President Biden staring at some pictures. On July 12th of 2022, we had launched in December 25th of 21, I was at NASA Goddard in Greenbelt, Maryland, ready for the press conference for the first science of Webb to be revealed. And 3 days before we heard, it's not going to be the first time. President Biden wants to show it first. Kind of hard to argue with that. So a handful of NASA scientists went to the White House, and on July 11th was actually when first science was revealed. In this picture, you see some incredibly odd things. And you see things like stretched right up into the right. I call it at the 2 o'clock position. It's called gravitational lensing. We literally are seeing universes or galaxies behind galaxies, where the gravity itself bends space-time and brings that image, and we have a powerful enough telescope to catch the light of something that you couldn't see except for the way that the light is, gravitationally bent around this other massive object. So you have these goofy things. I was literally walking in a place that had the TV on CNN, and about a month ago, we found something that looked in this, just because of the angle we looked at it, looked like a question mark. So now it's the question mark, galaxy in there. And it was cool because CNN had it as like, oh, Webb finds the question mark galaxy in there. Truth be told, if you went on the other side, it would look probably like a normal one, but it looks really cool, right, when you see it around there in there in the question mark galaxy. Plus, it was cool to walk by a TV and see the results of the program you worked on for 12 years being shown. And when my dad gives me a call and says, hey, pretty cool, I heard about, Webb. He was actually more humble when it was an answer on the Jeopardy question, I'll be honest, than when there was any scientific thing, because he watched a lot more Jeopardy than he does the news. So it's these types of images that are starting to condense things to like this. And in this case, you get, and this literally I think has the optics of both a dying star and a new forming star in there, right? So these scientific things, and none of you astronomers, astrophysicists can ask me a question, because I only know this is beautiful. I'm not an astrophysicist. I'm not going to tell you the science other than we're trying to find how the periodic table came to be. We're trying to look at atmospheres of planets to see that they have signs of life. But these are the kinds of things now that not only are living their life scientifically, they're becoming people's screensavers. They're being put in ads. They're the picture that they want to show. And don't be embarrassed by that. Somebody in here is going to be a marketing major, right? Sell it. Use what you have to your advantage. Get people hooked into it, right, and what it is. This one is really fascinating because I think this is Fomalhaut, but we're actually looking at another star, but it's occulted. And what we see is the rings, and those rings are disks where planets could form, where there's debris. And what they're speculating, if you look close to 3 o'clock, it's kind of hard, right in there. See how it looks like a little bit brighter in that part of the ring? There's a speculation as to whether we're actually seeing a planet being formed in a ring around a star. And only seeing the birth of stars, we've seen the birth of a planet in it, right, in this particular thing. And this is what happened when we get this much more data. It's pretty amazing. This is the fun part for me. Great to be in New York. I talked to some of the students who heard this already. But on July 12th, and I'm going to challenge anyone in this audience, some of you, all of you were born after 2000, I'm guessing, at this point in time. But there's other people in the audience that were closer to me that weren't. But in this century, your only century, what's the thing that has been celebrated as a good thing, so uniformly, so globally, that has ended up with the Empire State Building lit in the color of our iconic mirrors of gold, with Piccadilly and Times Square having it on there, with a Coldplay concert, and it as a backdrop as it's being sung, or students sending us their artwork, or bald-headed me right there in the bottom middle celebrating as the last mirror comes in. The Google Doodle, I don't think this is in here, on that day was, how it changes based on something, important there. All of that on July 12th. Headlines, New York Times, Washington Post. I challenge anybody from 2000 to 2022 on July 12th to show me something so positively celebrated. Because it doesn't. We tend to celebrate negativity or not celebrate it. We get drawn to it. It's what we put. It's how we headline things. You need to do good too, right? You need to understand what's going on in reality. But that's a pretty iconic day. My proudest right there was when I got to tell my friends who were living in New York, because I was actually in Maryland at Goddard when this happened, but still living in California. I said, oh yeah, that's because of the Webb telescope. Go look out your window, my New Jersey friends. And you can know, that was your high school buddy, who had a part in that. It's a pretty cool thing. So as always, I talk a lot. You heard a lot. But we're not going to let you out of here unless you ask a lot. So with that, I've explained a bit about science, a bit about Journey. Hopefully I communicated in English and you understood some of it. There's got to be questions that are just popping and you want to run to those mics. Somebody's going to walk to the mic. That's good. I didn't encourage somebody to run. But what I will do is ask you to say your name, where you're from, something about you, and I'll ask somebody to give you a sticker. Let me do that. See, I brought a red sticker for your computer. All right.
So my name is Kira Moser. I'm from Connecticut. My question is, so I know the Webb telescope is only going, it only has a lifespan of 20 years. So my question I have is, what are you doing now to make sure that it's not going to be just 20 years? And instead of you working, like, it took you 20 years to develop this one, and you're now working on the next step afterwards. So from Hubble to Webb to whatever.
Great set of 2 questions. So, it's going to last for 20 years. What are we doing to make sure that's better? And what are we doing that's going to be next? Let me explain what's life limiting in Webb really quick. Running out of gas. So, as much as we're in an orbit, not going to get, again, I promise I wouldn't confuse it too much, but for those who want to know, Lagrange point 2 is a place where the interactions of the planets and the moon are such that you kind of want to stay there. But you still drift, and we actually do an orbit around that point. With that, we have to keep the telescope. We have to fire thrusters and rocket engines to keep ourselves about that point. And our tank is only so big. Most of the hardware is designed for that will last beyond that. So the question will be, will we run out of gas? And that's about how efficient. So when we do an annual science cycle, because it was mentioned in the intro, we are going around the sun, 365 days. We plan 1 year of science missions, look, because when we're on this side of the sun, we can only look at those things. Mission planning will be a huge part of extending the life of this. Moving the smallest amount, right, to take observations. There is a chance we put what are called fiducials, spots on there, so that a robotic vehicle that somebody in this room is going to design is going to go to Webb, cut off the cap of his gas tank and fill it up. That's actually a very plausible thing to happen 20 years from now. Currently, we have not done that, right? We demonstrated a thing called orbital express with Darwin and others, but haven't really perfected the idea of refueling a satellite on orbit or somehow extend it. Northrop actually builds technology that brings the fuel tank up and hooks on. So there's chances that we can extend it. Then what will happen is like focal plane arrays, the things that catch the photons, they'll just degrade through the nastiness of the space environment, and then you're done. It is not designed like Hubble where the instruments could be removed and replaced, because it was so hard. The one thing we couldn't do was make electronics serviceable. It literally built up like a Swiss watch. You're not going to get to the part on the bottom without taking apart. The next thing after Webb, we hope, is a bigger, 2-3 times bigger than Webb, that will be able to look at habitable worlds, be able to look on the surface. And that right now was being requested by what's called the Decadal Survey of Scientists in the 2021 with COVID as the thing that they want in science, this type of thing. So we are doing the early designs of a larger one, and I think possibly that won't be one that's fully built on Earth. It'll be one built aiding with robotics, or possibly astronauts on orbit, where we can build, now that we've proved a segmented optic, can we bring part of that optic together in space and save it so we can do like a few launches? Because we haven't beat the rocket equation yet. No matter what it is, it's hard to get off Earth's gravity, right? And so that's where we are in the next thing, and maybe possibly a modular design buildable on orbit.
And so just one more quick one. Like, say 20 years comes around and you don't actually have a solution for refueling. Building the second Hubble Webb telescope, is that going to be cheaper?
Yeah, it's not. So, because we stopped. Making the second here, put this in your business school, or you got to do some, calculus. Making the second of anything is only cheaper if you're doing it when you're building the first. You have to have on some continuous production. Stopping and going back to anything is advanced, no doubt, by the engineering you do, but it's very hard to go back and recapitalize and do that. So the recurring cost would be no cheaper, maybe more complicated by having to overcome obsolescence. Things that you designed around then, it's not free to design those out. So it's very complicated to build a second. And NASA doesn't tend to do just more of the same thing. The real focus is to continue to advance.
Hello, I'm Josh Goldman, major engineering. And my personal question is, should we use James Webb to look at quasars?
Yes, Webb is, so looking at quasars, looking at any object in the sky invariably is confessing information in a broad range of wavelengths, right? From, I won't give them an order there, but the constant, cosmic radio waves is actually how we discover the beginning of the Big Bang, the Cobra Observatory. There's ultraviolet and optical and infrared, right, and the wavelengths of what we see there. There's Chandra X-ray, there's gamma rays. So Webb is just one narrow eye, and it all depends is how much quasar science actually has infrared knowledge in it. And that's where you lose me, and I fully admit I do not know, and some other smart people in this audience will find you after and answer that question. But if there's infrared information, if you're a smart person knows this, anyway, within the quasar and its spectrum, and that's enough to confess, like X-rays are for black holes, right, or infrared light is for the first stars, then absolutely could do it. There's nothing preventing us. There's only one star in the entire universe Webb is not capable of looking at. Ours. Because if we turn around, we melt. So literally, that optic that's cured to work at minus 400 degrees Fahrenheit is not. We'll be blinded and obliterated by our own sun.
Thank you so much. Thank you so much.
Hi, my name's Brianna. I'm a neuroscience major. And my question was a little bit convoluted, so just stay with me here. In the design for the Webb telescope, was it ever kind of thought of or brought up? Because I noticed how you guys fold it in so that it fits in the spaceship. But if you were to use a different material that was more easily collapsible, that had the same reflective properties as the mirrors that you did use, but kind of on the back of it, it's a bit of a web where you have components to adjust it so that if part of the...
I get exactly what you're asking.
But I'm not an engineer, but if you did something like that so that when you did put out in space and you expanded it, it could be bigger than this, because you still have the cooling component.
You want to work for Northrop Grumman?
I'm sorry.
You want to work for me? Come on, think about it. But
my dad already works, so I don't need...
I know your question. Could there be another way? And when you talk about bigger optics, there's all kinds of challenging ideas. We had talked about, and we still are, is there a more flexible surface with actually more actuators, more motors on there, where you can protect the surface through that? The hard problem we have today in doing that is all of those actuators right now need cables, and they need electronics, and they need motors to drive and all that stuff. The mass of actually creating the more flexible, bigger optic is prohibitive to our ability to launch that with today's technology. But with the ability to go into orbit and do assembly and have a deformable mirror. I was just talking to some smarter person than me, because we're at a conference last week with Northrop Grumman. Somebody's talked about literally using a liquid, and the liquid, due to surface tension, creates a certain thing, and then you could bend that through that. So literally, if you could take a water droplet and put it in there and control it and deform it, can you create an optic out of a liquid in space? Because in zero G, its surface tension is going to dominate, right, and do it. So there's people looking at items like that. They're looking at more what are called actuators, motors to do that. For us, we couldn't do it. We had a limit how many wires we had, how many motors we had. So we solved the problem by making the mirror as perfect as it took 8 years to make our mirrors. We would love to make them short. We were polishing atoms at a time off of the surface of this mirror. Each mirror is 1.5 meters, 4.5, 5 feet, flat to flat. Literally, in the term nanometers, we were better than 20 nanometers root mean square average of defect. That means the largest blemish on one of our mirrors was the size of a bacteria. It took us 8 years to make mirrors that perfect. And we still put motors on the back. So we will get there in your generation.
Additionally, with that question, would it be too, I suppose, like risky or not, like you don't have enough of a margin to fix it or whatever you want to call it, for it to be controlled by like one motor and then have the wires expanding like in that spider web type thing?
As long as you still had an actuation there, it still had to physically do something to be able to bend and move. And how do you attach it? And how do you control it to go in the direction you want and either tug or push? Is that going to be possible? Yes. Was it possible at the time we started designing this technology?
Okay, thank you.
Hello, my name is Aiden Smith. I'm an international business major. And
It's an international program.
yes. And first off, I wanted to thank you for coming here and talking about this. When you showed the pictures that Webb took, I remembered seeing it on Instagram, like the hub first.
Turns out we were on Instagram. I told my daughters that.
I follow NASA on Instagram, so I'm keeping up.
There's some influencer did some videos of me at South by Southwest last year, so take a look at that too.
I'll find you. But yeah, I was just so like awe-inspired. Like tears were literally coming out of my eyes. It was so beautiful. So thank you so much for all of your work. And I have like two questions. It's a bit of like a compound question. One, how interdisciplinary would you say that this entire project was? Like you brought up the technician, you brought up that even your own knowledge only goes so far. How far would you say that people were like certified, specialized, and like in terms of like what's necessary to complete this project, how much would you say that everybody knew almost everything about every little aspect? And two, when you were explaining that you literally had to talk to Congress about why, why we need funding, why this needs to happen in the first place, what language, what strategies did you use to communicate not only like the purpose of this, but like why they should care about it? Because I completely agree with you when you said that you don't want to like intimidate people, or you don't just want to make them say, here's money, shut up, get out of my face. You want them to care about it so they'll continue funding it and so they'll be interested in what you guys fund.
Absolutely.
How did you create the language and the space to do that?
So how interdisciplinary was Webb? Everyone in here would have been able to apply every one of your degrees, I'm truly telling you. And it isn't just engineering. Of course, I had chemical engineers looking at cryogenic materials, mechanical engineers doing composite structures, electrical engineers figure out how to make the dog go. I had accountants and business folks in finance helping me break work down into a work structure that was executable, so we knew we assigned $1 to do this and a day to do that, and how we're doing that. We're a public company, so as we spend this money, we don't have to report to NASA and our shareholders. How are we doing on that? Are we making money or losing money on this? So I have finance people help me survive the Deloitte audits, that would come through and look at the books as we do quarterly earnings. And I surround myself with all of those folks, and I ran a very flat organization where many of them had a voice at the table, as opposed to a very vertical organization where everybody reported under 300 people, and then I heard that. So I liked a flat organization with the voices there. When my engineers would come to the table, I wouldn't kind of make them suffer the stuff they didn't want to do, which was the business and accounting, and bring your business and account person with you so we can talk to this together, right? Use both of those. Learn from them. Don't dismiss that they're doing their job and you're doing yours. It has to be an integrated answer, but don't think you have to do it on your own. So incredibly multidisciplinary. 750 people, 80 to 100 business folks were on this team. So there's nothing that doesn't get done without understanding, especially you're making a commitment how something's going to cost at the time in there. So that part was easy. And your second question was communicate. So let me simplify the simplified communications. I'll give you two things to think of. One is, so the most important thing you got to take away here from right now for your next 4 or 5 or 6 years, whatever it takes to graduate. Don't just call up your parents when you need money. Because every time your number rings on their caller ID, they're going to know why you're calling. Call them up in the middle and say hi and you love them. Treat others who are working with you in a continuous relationship. If you only go back when there's a bump in the road and something more, as opposed to, here's what I'm doing. Or here's a time where I'm not actually asking for anything, I'm just giving you status. So I had a consistent message every 3 months for 10 years, meeting with folks so they were a part of the journey. And there was somebody else, and I'll use it, she was actually from Long Island, Pat McMahon, who said to me once, Scott, if every time you go to visit somebody and the first thing you do is you put your hand out, and you're asking for something, and that's the only thing you do, then they're going to know who you are walking the door. Sometimes put your hand out this way, or shake their hand. Just say hi. So create a consistent relationship, right, in which you do it. The second thing is, I always look backwards, today, and forward. So I would always have this, when I spoke to you last, here's the things you were doing. Did I get over the hump? Did I solve that problem? Did we have success? Here's what I'm doing today. How am I doing, right? And how does that mean, what does that mean, right, to what I'm doing in the future? And oh, by the way, the next time I see you, we're probably going to do the first deployment of that optic that we hadn't done before. Now they know something hard is coming in the future. So now when they come there and I say, we had a bump in that road, they say, well, at least I know you told me you were doing a deployment. You did it on time, but it was a little harder. Now what are you doing? That becomes that day's today, right? And then it becomes the next one, yesterday, and I explain how we solved that problem. So I was always, what did we do? What are we doing? What are we going to do? Always every 3 months, and not only out of necessity. So do not just try and engage people when you need them. Every relationship is built about a continuum. And if you stick to that, you can survive a lot of the bumps in the road.
Thank you so much.
And there's a NASA guy coming. All right, rocket.
Had to wear NASA hoodie, you know.
All right, hold on. I got to give you a web pin to put on your NASA sweatshirt. Look at that gold pin right there. Put that thing on it. All right, name, rank, serial number.
Hi, I'm Vanch. I'm a mechanical engineering with aerospace concentration major. So this is kind of the field I want to go into anyways, so I had to be here. But I had a question. I don't think we went over this, but what rocket was the telescope also?
Yeah. So we were launched on the Ariane 5 rocket by ESA, the European Space Agency. The Ariane Space is the provider. The Ariane 5, 100+ incredible success rate, launching out of French Guiana, which is near the equator in South America. So I was on console there. And that was picked because it was a part of NASA working with the Canadian Space Agency, who did some instruments. European Space Agency also did instruments. And in the United States, the public did not pay for the rocket ride. That was a contribution by the European Space Agency.
So were there other rockets also discussed, like such as the Falcon Heavy and other variants?
There was no Falcon Heavy when we picked our rocket in 2004.
Oh, so you guys picked it early.
Yeah, so we picked the rocket in 2004, and there's a very difficult equation called coupled loads, which is how does your thing on the top of the rocket react to the thing underneath it, which both has a vibration environment, so it's going to shake you violently, and it has an acoustic environment. When you go to a concert, you can feel sound, right? You can feel that sound. Same thing happens in rocks. You have to test things for an acoustic profile and a vibration profile, and you need to know how the rocket is going to perform, and you design around that. So you can't just throw another rocket in, even if it's capable, it can take your mass and you can put it in there. You literally design to set a coupled load cycle where you send your data to the rocket provider, and they shake it together in a model, and then eventually we literally do that on the ground. We put the entire telescope on a vibration table in 3 axes, X, Y, and Z, and we pummel this thing on the ground because we want to prove that it's going to work, or if it's going to fail, you want to learn from that lesson before you ever do it for the first time. It's called test like you fly. So the rocket was picked early on, about 2 years into the program, and then it was lock and load. We were coupled, so to speak, to that rocket.
Do you think if the program was starting now instead of when it happened, you would have chosen a different rocket that's available now?
I think the desire to also have an international partnership could have led to a similar answer.
Gotcha.
Because you're looking to find ways that other audiences to contribute, and that was a way that could be done. So hard to say. NASA made that decision. Ask your sweatshirt. But I believe it still would have been under heavy consideration to look at another rocket to be a part of this international partnership.
Thank you so much.
You're welcome.
Just going to say these will be our last 2 questions because we are bumping up against
All right.
last 2.
I just keep talking, so.
My name's Haley. I'm a psychology major, and I'm from San Francisco, so I have no idea how far DC is, but I understand San Francisco to LA. My question is, like, if it was so important, like, you had to wear the full suits and, like, to prevent hair and dust and everything from getting on the mirrors, how did you get it to your location without there just being hundreds of things affecting it?
Scarily. So when that telescope in the clean room with folks in their masks, gloves, taped around literally so there wasn't space going in there, you know, just their eyes right through there. When we transported when we did that scary thing that I told you, we went into a shipping container, we double bagged it, and constantly did what's called a positive purge. You take dry nitrogen as a gas, a very clean gas, and constantly pump it into that environment so that air is only going out, not coming in. So positive purge. So the entire time that trip was being made from the high bay in Redondo Beach, California, in a boat through the Panama Canal, first time I ever had a satellite go on a ship. Normally they go in an air transport like a C-5. We were bigger than the biggest military transport airplane. We actually had to go on a boat through the Panama Canal, come in. But the entire time we were in that shipping container, we were pumping positive nitrogen gas so that nothing could ever get in. So we started clean, we encapsulated clean, we positive purged, we took that all the way there. We got in another clean room, meticulously cleaned the external part of the tank, of the shipping container, took those pieces off, took it off, brought it in another clean room, and then took the bag off of it. So that's how it made its journey.
And then a second, smaller question, what has been your favorite part of this process, both like including the planning, the developing, launch, your results, like what has been your highlight?
Oh, I'll answer right. The people and the psychology of leading a team of 750 people. How do you motivate people in negativity? How do you get the best out of them? How do you get somebody to bring pride, but not ego? Because if somebody didn't want to get questioned when they turned the last wrench and put the last cable in a clip, and that clip hung up on orbit, I told my whole team, bring your pride in the high bay, but not your ego, because every operation you do, somebody's going to ask you to assure them you did it right. You need a second set of eyes to look at it. You need the engineer to oversee it. And how do you get people so motivated around something singularly that they, in fact, lose their self in it and just bring what they have? And leading a team, to me, no doubt, the best part of all of this.
Thank you.
And I would have said that to an engineering major, too.
Hi, my name is Christian Graziano, and I'm an accounting major.
My brother's an accountant, so I get you.
I was curious, for when the sun shield did get tears, were there any other reactions other than what did we do wrong? Like, were there worries of money?
It was huge. So when the sun shield was torn when we first came out of it, first of all, we had to learn, could we repair what was there? Was it, could we patch or do something? Then we had to fix preventing it. It was one of the many moments in time where people asked, did we bite off more than we chewed? Did we create a design that was not implementable, right? Was it only good on paper? So right there it is, you tried something, it didn't work, and until you have that solution that knows you can both fix it, because it's going to take time and money to do that, and if you can't fix it, it's even more time and money. And then can you prevent it? Because we had to fold it 3 more times on the ground. We had to do 2 more deployments and then the last fold to go on orbit. So yeah, it was a very challenging time. It's really easy to talk about now because all 344-point single failures worked really well. So, but in those moments in time, it was a challenge to say, well, maybe this won't work. And if people believe it won't work, why would you give any more money to it, right? Why won't you just cut the bleeding off there? So we really had to quickly say it was repairable. Thank God Doug Green talked about squidging and came out and said it's preventable. So we had to get both those answers. And there was a lot of pressure to get those answers right. And truth be told, if either of those answers weren't right, if it wasn't repairable, that may have been a little bit too much to bite off. Not saying it would. If it wasn't preventable, then invariably we would have stopped the program at that point in time. So yeah, there was a lot of shifts. Thank you, accountants, for that question.